Okay, so let's try and unpack this. Have you ever looked at a motor? Maybe, something simple like an electric scooter.
Hmm.
You see these numbers, how hard it twists, that's the torque, right?
Right. Torque.
And how fast it's spinning, usually in RPM.
Yep. Rotations per minute.
And you think, okay, how much power is this thing actually, putting out?
Mm.
It feels like it should be straightforward. Just multiply them.
You'd think so. But
Yeah.
then, yeah, you stumble across these weird numbers and
These
formulas.
magic numbers like 9550, or I've seen 5252
Yeah,
sometimes.
exactly.
Where do they even come from? And like,
Yeah.
how do you know which one to use? It gets confusing fast.
It really does. And that confusion right there, connecting torque, speed, and power,
Yeah.
especially with all the different units flying around, that's exactly what we're diving into. We've looked at some sources that lay out the basic physics,
Uh,
but crucially, they also show how a smarter way of handling the units just cuts through all that mess. So, our mission today is really to get a grip on that fundamental relationship and see how managing the units properly makes it, well, surprisingly simple underneath.
right, because the core physics is simple, isn't it? The sources show it's just power equals torque times angular velocity. P equals TW.
Spot on. That's the heart of it. P equals T omega. But like you said, the common hurdle the sources point out is speed. It's nearly always given in RPM.
Rotations per minute.
Yeah, but the physics equation, P equal TW, needs angular velocity omega.
Yeah.
And that's usually in radians per second.
Okay, so RPM is like how many full circles it does in a minute.
Exactly. It's a frequency.
But angular velocity is different, the radians per second.
Precisely. How many radians of angle it sweeps through each second. And since, one full circle is 2
By
radians.
the two,
Yep, and there are 60 seconds in a minute.
so you need to convert the per minute to per second.
You got it. Converting RPM to radians per second involves both that 2 and that 60.
Okay, so that's where those magic numbers come from.
Yeah.
Like the 9550 or 5252. Are they just bundling up those conversion factors, the 2 and the 60?
That's exactly what they are. They're pre-calculated constants for specific combinations of units. So if you want to put in torque in, say, Newton meters
Mm-hmm.
and speed in RPM, and you want your answer directly in kilowatts,
Yeah.
kW, you need a specific number that bundles the 2 par the 60 and the conversion from watts to kilowatts and handles all the units canceling out.
So the 9550 number often pops up for that specific conversion, EM and RPM to kW.
That's a very common one, yeah. 9549 point something, if you want to be more precise, often rounded to 9550.
Ah, I see now. And the 5252, is that for different units, maybe like imperial?
Exactly. That one typically shows up when you're working with torque in foot-pounds, pound-BFD, and speed in RPM. And you want the power directly in horsepower.
Right. Different units, different magic number. This is making sense.
Mm-hmm.
And the sources we looked at, they really emphasize that using a tool or an approach that understands units makes this so much easier.
Oh, massively easier.
Because you can just stick to the pure physics equation,
Mm.
P equals TW.
That is the absolute key insight. Forget memorizing those numbers for every possible unit mix. You
Yeah.
just use the fundamental equation, P equals TW. You tell your system, okay, my torque is, say, 5 Newton meters. You write 5 Nm
With the unit.
with the unit, and my speed is 1500 RPM. You write 1500 RPM. And if the system understands units, it does the conversion from RPM to radians per second automatically behind the scenes.
Just like in that example calculation, one of the sources had it use T equal 5 Nm and N equals 1500 RPM.
Mm-hmm.
And it showed calculating omega first. So taking 1500 RPM, the system converts that to rads. What was it, about 157?
Yeah, about 157.080 radians per second. The system handles the 260 factor.
Okay, and then you just multiply P5NEOS times
Mhm.
157.080 rads.
Simple.
Dead simple. And the beauty is, the answer you get automatically comes out in the fundamental units of power, which are watts in the SI system.
Right, watts. So in that example, it was 785.4 watts.
Exactly.
Yeah.
Which you can then, easily display as kilowatts if you want, 0.785 kilowatt.
Yeah.
No magic number needed. Just the physics and letting the units sort themselves out.
That's it.
And what's really cool is that this framework, torque times speed equals power.
Mm.
It works everywhere, doesn't it? That little scooter motor or a massive industrial pump or, I don't know, a car engine.
Absolutely. The physics relationship is universal for rotating systems. You just plug in the specific numbers for that machine, making sure you include their units.
That's what the sources mean by unit freedom, I guess.
Precisely. You define the core physics, P, TW, just once. Then you can treat it almost like a reusable app. Need to use foot-pounds and RPM today? Fine. Input them. Want the output in horsepower? Just ask for it.
Okay.
Tomorrow, you might have M in hertz. Same equation. Just tell it you want the result in kilowatts this time.
No need for a different formula or trying to remember which magic number was for which scenario?
None at all. It takes away that whole layer of potential error and, frankly, annoyance.
Yeah, makes it faster, definitely less error prone, and you're actually thinking about the physics, not just plugging numbers into a weird constant.
You're focused on the relationship, not the arbitrary conversion factors.
And that 0.785 kilowatts for the scooter motor example, that translates nicely, doesn't it?
It does. As the sources mentioned, 0.785 kilowatts is actually pretty close to 1 horsepower. Just slightly over, technically, but roughly one.
So that little motor twisting with 5 N meter at 1500 RPM, it's giving out about 1 horsepower.
Yeah. It kind of gives you a feel for it, connects the calculation back to something maybe more intuitive, that historical measure.
That's pretty neat, puts in perspective. So wrapping this up then, what's the big takeaway for you listening? Well, first, understanding that core link. Torque times angular speed gives you power. That's fundamental.
Definitely. But the second big thing is realizing that most of the perceived complexity, it's just unit conversions.
Right.
And if you use tools or methods that handle units automatically, you can completely bypass those confusing magic numbers like 9550 or 5252.
Makes life much simpler.
It really does. It lets you, as we said, have unit freedom. You can just think in physics.
You focus on POTW and let the system handle the unit bookkeeping.
Turning what feels complex into a clean, reusable approach you can apply to any rotating machine you encounter.
Which leaves us with a final thought for you to chew on.
Mm-hmm.
If that example motor, 5 nanometer to 1500 RPM, is putting out about 1 horsepower, roughly like riding a horse, metaphorically speaking,
Right.
how much horsepower are you actually interacting with in the everyday machines all around you? Think about your car, maybe your kitchen blender, power tools.
Yeah, what kind of power are those things really delivering when you look past the marketing and think about the physics? Good question to ponder.